Okay, so now we've learned a little bit about displacement, average velocity, and the like. We're going to get into a little bit more depth, and the math is going to start coming a little bit faster now. Okay, we've talked about the difference between average velocity and average speed, but now I want to talk about instantaneous velocity. Okay, instantaneous velocity is where we start using calculus. Good times, good times. All right, so now let's take a look at a graph of position versus time. Now, position here is x, time is t. So let's say we have a position versus time graph that looks something like this. This will be our x, I'm going to call it x initial. I'm going to call it x final instead of x1 and x2. X initial and x final, x0, xf, a little bit more descriptive. Okay? Now, in order to figure out, and this gets into a little bit of the graphical techniques that we'll talk about later in another video. Let's say I want to take a look at the average speed here. The average speed is going to be the initial position, the final position, the time it takes you to get there. So now my average velocity will be x final, that's x2, minus x initial divided by t final minus t initial. Delta x over delta t. Okay? Well, if I look at this, this is, think back to my math days, this is my y-axis and this is my x-axis. Okay? This right here, even though it's x, okay, that's really my change in y. Here, even though this is the t-axis, it's really my change in x, going back to your y and x axis in your math days. This is the slope. So the slope of a position versus time graph is your velocity. Okay? Now, here's the thing. If I take a look then at this, the slope of this line is my average velocity. All sorts of things that you can pull from, you can cull from that. You know that somewhere along the line, this has to be going at that average velocity. Math teachers like to spend some time with that. But really, the average velocity is useful, but not as useful as some other things. What if I wanted, instead, to find the speed at this point right there? Here's the thing. I know I am going a lot faster when I'm here than my average velocity is here. Okay, it's my average velocity is not as much as my velocity when I'm here. Okay, I know the speed is greater and I know it's positive, so the actual velocity is more. Let's just say that this occurs for some. Let's just say that this is at t equals 5 seconds. Okay, I'm just pulling that out of a hat. Okay, pulling that number out of a hat. I want to figure out what the velocity is at that 5-second point. So now, what we say, okay, the way that we describe instantaneous velocity is this v of t. No, that is not v times t. That's your velocity at some time t. This is your instantaneous velocity. Instantaneous velocity. I call it instantaneous velocity so that I can spell it correctly. I can do math very well in my head. My spelling is atrocious. So now, my velocity at 5 seconds. So now, let's just say that I did this. V at 5 seconds. If I wrote that, this would be my velocity at t equals 5 seconds. Okay, that's what that v parentheses 5s means. It's my velocity at 5 seconds. Again, it's not velocity times 5 seconds. Okay, it's my velocity at 5 seconds. So now, if I was going to do this, if I wanted to figure this out, right, a couple of things I could do. Okay? If I don't have any knowledge of calculus, and I wanted to figure out the velocity here, I know that the slope of a position versus time graph is velocity. So I can kind of creep out a little bit to the side here at that position, creep out a little bit to the side over here, right there, and I can look at my position at this location and this location. Okay? This would help me get my average velocity. All right, I take a look at my a little bit before and a little bit after. I look at the position, and that change in position with respect to time, I'd be able to pull out my average velocity. Okay, over that time period. But it's still not my instantaneous. What I want to try to do is squeeze this down as much as possible. I want to squeeze that interval down as much as possible. Now, here's the thing. I can't make it zero using normal techniques, all right? Using standard algebra. Because what happens is, my velocity at 5 seconds there would equal my change in x over change in t. If I make this interval extremely small, okay, and I'm using normal algebra techniques, that delta x is going to be 0. My delta t is going to be 0. That doesn't work. 0 over 0. 0 over anything is 0. Anything over 0 is infinity. So I've got 0 and infinity. This is equal to both 0 and infinity at the same time. That's not possible. Okay, and I say, what can be done? This is where calculus comes in. And this was one of the great triumphs of the human mind back in the 17th century using, I guess, Leibniz and Newton were really big in this. And it was the introduction of limits. Okay? So now, what I'm going to do is say that my v of t here, my instantaneous velocity, okay, is going to equal the limit as t approaches, as delta t approaches 0 of delta x over delta t. Okay? It doesn't actually equal that. It doesn't actually equal 0, it approaches 0. And that's a very big difference to a mathematician. What we do is kind of use the tricks that mathematicians have developed over the years. So now, what I'm going to say, when you use the result of this, you don't have to take a limit each time. I'm going to say that this is equal to what's called dx over dt. Think of that d as very much like the triangle when we're doing delta x over delta t, except for this is over an infinitely small period of time. Okay? Infinitely small distance, infinitely small interval of time, and that's where the calculus comes from. Hopefully you're able to meet with Mrs. DeMail over the summer, and you're able to learn a little bit about calculus if you haven't already taken Calc 1. If not, I will put out a separate calculus so you can understand what we can actually do with this. And we're going to do a couple of sample problems later on. Okay? But for what we're going to do is say that the instantaneous velocity is equal to delta x, dx over dt. That is the calculus version of delta x over delta t. Okay? So now, moving on, all right, we have acceleration. Now, acceleration is to velocity what velocity is to position. We're looking at a change in velocity with respect to time. Okay? Now, what we taught, how we described acceleration last year was very similar to how we described velocity. Okay, where velocity was a change in position with respect to time. Acceleration was the change in velocity with respect to time. And again, this is average. And for the entire last year, we used a constant acceleration. Okay, so the velocity would change at a constant rate. We're going to take it a step further this year. We're going to look at instantaneous acceleration and see how that works. Now, very similar to what we did before, we're going to say that my acceleration as a function of time, my instantaneous acceleration, okay, just like we did with velocity, my instantaneous acceleration is going to be dv dt. Again, instantaneous acceleration. Okay. So now, I have another way to look at this, by the way, is to say my acceleration as a function of time. For those of you who are already calc savvy, for those of you who are not, don't worry about it. It's not that big a deal right now. It's the second derivative of position. Okay? If you're not calc savvy yet, don't worry about it. You will be shortly. Okay? Or take a look at the video on calculus. Okay? So my instantaneous acceleration is the second derivative of position. It's the first derivative of velocity. Now, as far as what we are going to take a look at here, the first thing I want to talk about is using a constant acceleration. Now, I wanted to set this up. I wanted to get this out there. We will use it, and we will use it extensively. All right? But there is a special case, and we studied it all last year, so I'm going to go through this proof pretty quickly. In talking about a constant acceleration. A constant acceleration has is very important, and we see it again and again and again, and it is a very important special case. Okay? It's not one of those special cases where you're assuming no friction, when there's always friction. Okay? Constant acceleration we see again and again and again. From the simple case of this, okay, to being able to take a look at a car where we are modeling it as a constant acceleration. Where, you know, that's a case where, like friction, we're assuming that there's no friction, and there really is. Car's acceleration is not always constant, but we can model portions of its trip as a constant acceleration. So now, mathematically, the way we would say a constant acceleration the way to describe a constant acceleration would be to say that my average acceleration is equal to my acceleration at any time t. Okay, that's just a mathematical way of describing it. So this is just saying it's a constant acceleration. And now we're going to take all those equations that we've learned, and we're going to kind of expand them out a little bit. And we're going to learn how to manipulate them around so that we can find what we need. So now, let's take a look at position when we have a constant acceleration. We have position when we're dealing with velocity. We have velocity when we're dealing with acceleration. But now we want to tie together our position and our acceleration, specifically when it's constant. Okay. So now, my acceleration is equal to change in velocity over change in time. Okay? And it's constant, so we can say delta v over delta t. There's no reason why we have to make it dv dt. Okay? And this will be v2 minus v1 over t2 minus t1. Now, in almost every case, you're going to make the initial time 0. So we're going to say that this is equal to 0. And I'm going to set t equal to t2. That way I don't have to write t2 over and over again. When really we just know that we're talking about the time interval over which this takes place. So now I can say my acceleration is equal to v2 minus v1 over t. My initial velocity might not be 0, and that's very important to take into account. Now, I can rewrite this, okay? I can take this, multiply both sides by t, add v1 to both sides, and I'm going to say v2 is equal to acceleration times time plus v1. And now you say, well, Mr. Folks, wait a second. How did you get from here to here? Well, I used algebra, okay? I'm going to be teaching you guys physics, especially in this type of situation where I make a leap from here to here. This is where I want you guys to hit pause and you yourself get from here to here, okay? I told you how to do it. You're going to multiply both sides by t. You're going to add v1 to both sides. But I want you guys to do that as part of your going through this lecture, okay? So now, let's take a look at position. Well, here we're able to take away average acceleration. We can just call it the acceleration because it's a constant acceleration. I don't have to call this average acceleration. It is constant. Okay. So now, well, let's take a look at position now. Now, position, something different happens. I have my average velocity is equal to, very similar to what we had before, x2 minus x1 over t2 minus t1. Now, I can break that apart just like I did here, okay? And I can say that my average velocity is equal to x2 minus x1 over t. And I made those two lines a little close there. It's not divided by, I'm just separating those two. Okay, and then I can rewrite this. x2 is equal to my average velocity times time plus x1. Now you say, well, here you took away the average acceleration. Here you didn't take away the average, you kept it as average velocity. Yes, I did. Okay, in this case, my velocity is changing. My velocity is changing, my acceleration is not. So I still have to keep this as average. All right. So now, let's take a look at average velocity. And we talked a little bit about this last year. Okay, and it's a very important aspect of it. Let's take a look at a graph. Again, looking at graphical techniques before we really get into the whole graphing concept here. Let's take a look at my velocity versus time. If I have a constant acceleration, if and only if I have a constant acceleration, my graph will look like this. Okay? The slope of a velocity versus time graph is going to be acceleration. Okay, we'll talk about that more when we get to graphing. Okay? Because I have a constant acceleration, I have a constant slope. So now, what this means is, if this is v1, and this is v2, so I have v1 over here, and I have v2 over here. My average velocity is going to be halfway in between. So now, my average velocity here is going to equal v2 plus v1 divided by 2. It's just the average of the two. This is, when you have a constant acceleration, you can say that your average velocity is just the average of your starting and your ending points. So it's going to be right here. That is average velocity. So now, I'm going to take advantage of this fact, and I'm going to plug it in here. So now, let me go back to the red marker because I'm doing this proof on. All right, I'm going to plug in. So now, this is x2 is equal to average velocity, v2 plus v1 divided by 2. v2 plus v1 divided by 2. times that time plus x1. Okay, so now we're getting somewhere. I've got, still though, it's still just position and velocity. I don't have acceleration in there yet. And then I look back and I go, oh, wait a second. I have V2 and V1. If I substitute in for V2 over there, I'll be able to pull in the acceleration. So now x2 is equal to, again, I'm just going to substitute in here. Acceleration times time plus V1. That's what V2 is. So V2, it says, plus V1 divided by 2. All of this times t plus x1. I'm getting close to the edge there, so I'm going to smooth that over. So now I'm just going to rearrange. By the way, again, hit pause. Get from here to here yourselves. Now, you hit on pause, you're going, hit pause again after I do this. See if you can make a prediction as to what happens next, where I get to. So now, x2 is equal to, this is AT plus AT times t divided by 2. That's 1/2 acceleration times time squared. V1 plus V1, that's 2V1. Divided by 2, that's V1. Multiplied by t. And then I have plus x1 over here. This is big dog. Again, I've told you this before. Do not go to your professor in college and say, I just plugged it into big dog. They will look at you like you have 3 heads and then go, you're an idiot. Okay? Big dog is a Middletown thing. Just, we have a way to remember this equation by. Okay? So, but that is big dog. All right. Now, the next portion of this is pretty straightforward. Okay? This is the equation, by the way, this is the equation that we use when we're trying to relate position and acceleration. Now, we don't have to use this equation per se. We might set it up a little bit differently. Okay? We might, there's all different ways that we can manipulate these equations. All right? Don't be wedded to just big dog. Okay? This is just one example of how you can manipulate these equations to get something that you want. All right? You have to be able to take that to the next step and work on other types of problems. Now, the next section, all they talk about is constant acceleration when you're talking about free fall. Free fall is what you have when it's just gravity acting on something. So, while this is in my hand, it's not free fall. When this hits the table, it's not free fall. Everything in between is free fall. In that specific case, we're going to say that the acceleration is equal to 9.8 meters per second squared. Some places will use 9.81, some places will use 9.806. 9.8 is just fine. We have 2 sig figs. We don't really worry about sig figs as far as the AP test is concerned, so I'm not going to stress it with you guys. Okay? Well, our next section is going to be coming up, and it's going to be looking at graphical techniques.